Hi everyone, and welcome to today's Tech Talk on inspecting and commissioning commercial scale solar photovoltaic systems. My name is Liz Fisher and I'll be the moderator for today's session. And as you know, throughout this Tech Talk today, all the phone lines will be muted. This will help to minimize all the background noise and feedback that we get so we don't have to hear any barking dogs. So when you first joined the Tech Talk today, on your control panel, there appeared an arrow up at the top right-hand side of your control panel. This arrow allows you to minimize and maximize your control panel. Also on here is a place for you to ask questions. Make sure you use this panel to send us any questions. We'll take them throughout the presentation and make sure we can get them to the speaker. Speaking of which, our today's speaker is Matthew Peladosi. See if I can get this right. He's a senior associate that manages Cadmus Solar Field Operations and oversees solar photovoltaic installation inspections, design, reviews, and electric code compliance. He has more than 17 years experience in the electric field and more than 10 years of experience providing energy conservation solutions and renewable energy consulting. He is a licensed electrician in Massachusetts, Rhode Island, New Hampshire, and Connecticut. He is also NABCEP certified in PV system inspector and has inspected over 600 solar PV systems throughout Massachusetts, Rhode Island, New York, and ranging from small residential to large megawatt facilities. So with that, I'm going to turn it over to Matthew and let him get on with today's presentation. Again, make sure if you have any questions to put them into the question box and we'll get to them throughout the presentation today.
All right, thank you, Liz. So yeah, we'll be discussing inspecting and commissioning PV systems, and in the next 20-30 minutes or so, we're just going to give you a high-level overview, basically my personal point of view as to how we do things. We'll show you a few learning experiences, things that we've learned over time, and things that you can pass on to your installers. So I'll give you a very brief background about the Cadmus Group if you're not familiar, then we'll dive into the content. So a little bit about Cadmus. Basically, we're a strategic and technical consultancy compelled to help solve the world's most challenging problems, strengthening society and the natural world. So we have over 700 professionals throughout the country and beyond. My team consists of about a couple of dozen people. We focus on this technical due diligence where the field inspections and commissioning comes into place. We also do design reviews, feasibility studies. On the policy and financial end, we look at power purchase agreements, net metering, program design and evaluation. And then we also get heavily involved with external trainings for code officials, solar installers, as well as first responders. And we were recently approved, NABCEP approved provider for continuing education credits. So Liz had already gone through my bio, so there's a great picture of me, so you can put a face with the name as we go along here. But that's basically where I'm used to, is up on the rooftops or out in the fields. One other thing to mention here is I'm on the executive board for the International Association of Electrical Inspectors, our Boston chapter. So we work very closely with the electrical inspectors, help educate them, as well as work with them on these solar installations as well. So we find ourselves as typically an independent third party where both the solar installer or electrical inspector can rely on us for some unbiased information. So as we dive in, again, we'll be talking a little bit about our process, touching high level on the things we cover, and I'll give you a few examples of everything or some things we find. But as Liz had mentioned, really feel free to type in some questions. I hope for a real healthy Q&A session at the end. And if you forget to do that or don't get a chance, don't be bashful to reach out to us after the fact. We're more than happy to answer any questions you may have about this presentation. So when we think commissioning, the inspection and commissioning process typically includes National Electrical Code compliance, equipment verification, that's basically counting the modules, looking at the DC output power rating, looking at the make and model of inverters and other equipment. It's going to include a visual inspection of the physical production, making sure all the connectors are plugged in and nothing is out of place. It's also going to include field testing. So we're going to touch upon all of these bullet points and illustrate exactly what they are, but basically give more definitive answers to if a system contains issues. So basically we're going to look at visual inspections. Does it physically look right? Does it comply with the codes? We're going to show you how to measure production. Is it producing the amount of energy that they claim it's producing? And then really get our hands dirty with this testing. So we'll show you what that's all about. The first bullet point, code compliance. Basically what we're doing is, this is more of the inspection aspect. So very similar to what the electrical inspector would do as well. We're going to typically be a lot more thorough with that, really open up every enclosure, look at every single part of the system. But we want to make sure that every aspect is in compliance with the National Electrical Code. And each state has their own adoption. Several states are on the 2017 edition of the Electrical Code. Others are on the 2014 edition, and other states might be on an even earlier edition. Like I said, we want to inspect all of the components. We also read a lot of installation instructions, probably more than I would like to admit, but to really understand how something is installed, it's so important to fully know the instructions front and back, make sure they're followed. So the code itself, the electrical code, contains many articles that are relative to PV installations. There's two sections dedicated to solar PV per se, but there's also several other articles that would apply. So we try to make sure we are aware of all of these articles and that we cite the appropriate articles if we do see issues. That said, too, when it comes to equipment, there are many different types of modules, racking, and inverters, and they all have, or they all can have, very different installation requirements. So again, it's looking at those two aspects, looking at what the code says, but also looking at the unique equipment's instructions to make sure we follow them properly. Equipment verification, this is going to be something where much easier said than done. So on these typical commercial scale solar installations, there could be thousands of PV modules or solar panels. We use that term interchangeably. So what you're looking at is probably a few hundred in that photo to your lower left there. And in order to truly document the system size, we need to basically count every single one of those, and what we do is spot check the nameplates. So the nameplate on the right-hand side, you can see that each one will have a maximum power rating, or Pmax. That's typically the rating we go by when we talk about the system size. So in this case, it's 260 watts, and say if we have 100 solar panels or so, we would just multiply that together and get the final DC nameplate rating of the system. So it might be cumbersome to count hundreds of modules, but again, it's important to verify that the proper equipment was installed. Once we can get the count, get the nameplate information, then that's how we verify the system size. Beyond that, it's going to be very difficult. But again, we look at that, and in some cases, again, we spot check the nameplates because we could have systems with 1, 2, 3, 4 different types of modules or different size PV modules. So that's another really important consideration here. Production. So beyond the codes, beyond installation requirements, will the system physically produce the amount of electricity that it's intended to? So there's a few different factors when it comes to production. There's shading, which is the most obvious. If the modules are obstructed from the sun, then obviously it's not going to produce that energy. So we'll show you a few ways to measure that. String configuration, basically these modules individually produce a certain amount of power. We string them together, very similar to a string of Christmas lights per se, where you have one light that goes out, you'll potentially lose the whole string. Solar panels are very, very similar, where if you have one or two modules shaded, you might lose that whole string. So that string configuration is very important. Also placement of inverters. So that's basically the component that converts the DC energy to AC. Again, we'll talk a little bit about the placement, ideal placements, and not so ideal placements. For string testing, again, as part of the commissioning, everyone has a different definition of commissioning, but in most cases it will include all or most of the following, and these are basically electrical tests. This is something where this level of detail, it's going to be very accurate, but it also has an associated risk. So it's important. We use licensed electricians for this application. We follow NFPA 70E for safety equipment. It's important we wear our voltage-rated gloves, glasses, arc-rated clothing, and so forth. But again, this is really diving into the system. As you can see on the right-hand side, there's several different tools that we would use to take these measurements. The first one, IV curve, that's going to be the most common. Basically, for any given string, the IV curve trace will tell us that the strings are producing properly or if they're not. This basically measures the current voltage curves of the modules and strings and then compares the results to the module specifications. So in other words, if a module has a certain curve, we can compare these results and see very quickly, gee, we're not getting the same curve. Why is that? Is there a tree right in front of the modules, or is something not connected properly, or is there something else? So that's a nice physical way to see if is it really operating as it should be. The next one down, the open circuit voltage. Again, that's basically just taking a voltage reading. Every module, on average, is going to produce about 40, 50 volts DC. We string them together in series, and Engineering 101 tells us that voltage in series adds. So we know we have a very good idea what that expected voltage should be. So we basically verify that. We test every single string to make sure that we get right in that range, and we flag any voltages that are out of that range. So we want to make sure that they match properly, and like I said, we flag anything that's not. Thermal imaging, the next one down there, really excellent tool, as I'm sure all of you know outside the world of solar. These thermal imaging cameras are really great when it comes to almost any type of commissioning. Same holds true for solar PV commissioning, but really it can be used to see hot spots on the array. On the modules, we can see if modules are operating properly or not. Electricians, we love thermal imaging cameras for our conductors, for our fuses or circuit breakers to see if they're running hot. Our terminals, if the terminals are running hot, again, it's not something we want to just go stick our bare hands on, but we can safely evaluate that through these thermal imaging cameras. Identify a hot spot, and typically that's a good sign that there's an issue. So nice safe way, nice accurate way to determine if there's an issue. Also, this insulation resistance test, it goes by the trade name a Megger test. Megger is one of the brands that of this piece of testing equipment, but basically we're sending a high voltage through these conductors and measuring that insulation resistance just to make sure that the conductor insulation isn't damaged or hasn't been jeopardized during the installation. And we'll show you some photos of what that looks like. Lastly, again, we need to ensure that fuses aren't blown. So we're going to be measuring fuse continuity as well for each of the strings. So it's very common that each string has either one or two fuses associated with it. And we'll either physically measure the continuity or do our voltage testing through the fuses to basically hit two birds with one stone. So now we'll just touch upon some issues that would limit production. So again, we touched upon these already, but we'll give you some visuals here. Most common one that we would see, and most common limiting production, but really least common on a well-designed system, is going to be array shading. So sometimes it's obvious, like this photo here, where it appears to be in the middle of a sunny day, and we see that half of this array is in shade. Shade drastically reduces the production. And like I had mentioned, even shade on 1 or 2 modules, you'll lose the whole string. So if each string is, say, 3 kilowatts, you lose 1 or 2 modules, that whole string will go down. Now, this is something that we can measure ahead of time via a shade analysis, we call it. So basically, this tool on the left-hand side here, this is one example. This is a solmetric sun eye. And basically, the sun eye uses a fisheye lens to capture the skyline. So we arrange this tool due south. It has a GPS in it. It has a compass. Line it up due south, and then it'll take a snapshot of all the obstructions. So as we can see here, and this might not be associated with this actual photo, but as you can see here, there are several trees that are blocking this grid here. This grid shows you the solar access from 6 in the morning all the way to 6 at night, and basically every month. So if I put this in the middle of the day, say in September, the sun would actually show up right around here. So it's a really cool, simple tool to use, and it'll tell us. So what we do is this will shade any obstacles in green, leaving all of the yellow, and the ratio of green to yellow would be the solar access. So we take this reading, we take the tilt and orientation factor into account, and then we get a what's called a TSRF, or total solar resource fraction. And basically what we're looking for, best practices over 80%. Some programs that we inspect for will say even over 70%. But basically it's the tilt, the orientation of the solar array, and then this shading factor as well. So we want to make sure that it has good sun exposure. And again, with this tool, we're able to measure either before or after an installation to ensure compliance. Next, from time to time, we do see some shattered modules. They will still produce electricity, but just not at their full output. The modules themselves, they're made of a tempered glass similar to our windshields. So in most cases, a shattered module will, the glass will stay in place. Obviously, we don't recommend walking across the modules or anything like that, but it's just another thing we look out for during inspections or commissioning. Again, walking the array, just part of that visual inspection. Do we see any physical damage? Another consideration, we see this from time to time. What we're seeing here are DC connectors on the PV conductors. So a lot of these are field terminated. You use a special crimp tool to crimp on an end, and then it plugs into this particular connector. And what we're seeing here, in this case on the left-hand side, and in this case on the right-hand side, is that the wires actually pulled out of that connector. So if power was going through there, that would basically create an arc and probably some sort of hazard. So it's something that we see from time to time. It's not something that while the system's running, we want to go pull on these connectors, but during the installation, this is basically where to verify that they're using the proper tool, they're using the proper connectors. These connectors, the brands of the male and female match up. There's several different brands out there, and some brands don't play nicely with others, like anything really. But again, it's something before the system started up, we want to verify that these connections are made properly. After the system's up and running, it's extremely difficult, if not impossible, to verify this. Also could be dangerous if, again, we start pulling on connectors where electricity is flowing through. It's like disconnecting a fire hose while water's flowing through. It's not a good idea. Once in a while, a visual inspection will show that connectors were either unplugged or more likely they forgot to plug them in. So the way these connectors work, you actually need a tool to open them or unplug them. So in this case, these installers might have just forgotten to make that connection. So an open circuit voltage reading will show this most likely. So and some other testing will show it as well. So again, we give it a visual, we could see that it's disconnected, but when we take voltage readings, we should see an outlier on this particular string. So another indication that this was not made up properly. And in this photo on the right-hand side, really tough to see, but you can tell this is a solar junction box or a pass-through box. So what we're showing here, again, a little difficult to see, but one of the black wires coming in from this conduit on the right loops around and then dead ends right over here instead of plugging into this terminal right here. So again, very difficult to see in the field, but this could be a result of troubleshooting when we get an outlier for that voltage test that I had mentioned. So that's one of the things that we would look for. And then blown fuses, again, just like a fuse, say, in your house or a fuse box or circuit breaker, during the commissioning, we test for these blown fuses as well. And instead of just replacing the fuse and hoping that it doesn't blow, we work with the installers to identify, okay, well, why did the fuse blow? Which usually a blown fuse would indicate some other trouble. So it's important, gee, maybe we replace the fuse, but then we keep an eye on that string. We really want to investigate why that fuse blew and not just blindly replace it. In this example here, what we're showing, this is a close-up of the fuse terminal inside the inverter. So what we can see here is a discolored screw, and then we look more closely on the left-hand side, we could actually see some thermal damage from this conductor. And actually, this connection was very loose, it heated up, and that caused the fuse to blow. So the problem could have been literally inches away from the fuse. So in that case, our investigation showed if we replace this termination, we should be in good shape. So again, one of the things we look for is making sure that verifying electrical connections are absolutely perfect. They're a common point of failure. So we want to make sure, again, through thermal imaging, through torque verification, that they are made up properly. Next on the list, and we see this again on the larger commercial scale solar PV systems, is issues with thermal expansion and contraction. So long runs of conduit across the building where, again, we're up in the Boston area, we're going to have very high temperature variations. Say in the morning it could be snowing, in the afternoon it could be 60, 70, 80 degrees out. And I know other parts of the country will be exposed to similar, but even over the course of a year, you have that metal, or sometimes they use PVC conduit that expands and contracts. And there's tables in the electrical code that allow a certain expansion and contraction, but then beyond that, you need a special fitting to account for that. So what we're looking at here is this. This is an extreme example, but this conduit had actually shifted over to the left approximately 10 feet due to the thermal expansion and contraction that had gone on. So that's why, again, doing a little bit of math, looking at the electrical code, understanding if we do need the proper fittings to account for that. This next photo, the scenario was slightly worse, where we had expansion and contraction. And this one, again, a long run, probably over 200 or 300 feet, if I remember correctly. But we also noticed that this, if you look at the different color rooftop here, I believe it crossed a building expansion joint as well. So this may or may not have been from thermal. This could have been from the normal building expansion, which would require that fitting. In this case, the conduit pulled out and started to cut into, this is the ground wire, luckily, and we started to see some insulation cut on the DC conductors. There's another situation probably about 10 years ago in Bakersfield, California, where there was an incident very similar to this, but with very unfortunate results. And you could look that up online. But basically, that was kind of the first of the learning experiences that this type of metal raceway needed those fittings. So there was a fire incident in that particular case. So again, just something that design issue, and then we also would catch this during inspection or commissioning as well. We'll touch upon a few different safety hazards now that we've encountered. First and foremost, and probably in my mind, one of the easiest to avoid is conductor protection. So we've got live DC conductors all over the roof, all over the array. In most cases today, these systems are operating about 1,000 volts DC, or they're designed for 1,000 volts, maybe operating around 800 or 900 volts. We want to make sure these conductors are properly protected. So in this case, it was a very poor raceway choice, raceway design, and we can see that these conductors are directly against the sharp edges of the racking. So it's just super important to consider the external effects on these conductors, making sure that they're properly protected from physical damage or abrasion. This next slide you'll see here, this is a ballast block. You've seen these in a few other photos, but basically it's a concrete paver. And up in this area, the most common installation method on a flat roof would be what's called the ballasted PV system. So typically not on high rises, but on the lower 1, 2, maybe 3-story rooftops, we'll see this. These concrete pavers, they hold the array down to the roof. They're great because there's no roof penetrations. However, you do have added weight to the roof, so our structural engineers would need to get involved. But also, we need to consider they're abrasive, and we need to consider protecting these conductors against these abrasive edges. One of the things to think about with PV systems is they don't only need to last, say, today or tomorrow, but also these are going to be installed for the next 20 plus years. So will this installation method hold up? That's what we think when we look at these installations. And then this is an unfortunate result of a loose connection that was not found prior to starting up the system. So in some very rare cases, we see some of these unfortunate events. Again, thermal imaging. In this example, the main PV breaker, which was right in this location here, this is a PV panel board, or what we call an AC combiner, basically bringing a bunch of inverters together through these circuit breakers on a very large system. But it was undersized for the expected load. So normal operation was very close to its limit, its current rating, but it caused excessive heat. So it wasn't enough current to trip out the circuit breaker, but enough to cause excessive heat. So this connection, this electrical panel, was very hot to the touch, and we found out that this breaker was not sized properly. So typically when we size these loads, we're going to size them for 120% greater than their capacity. So that way they'd be operating at normally no more than 80% or so. Electrical terminations, again, same consideration. In this case here, every terminal that we tighten the conductor down, or any electrical termination, there's a specific torque value that we need to follow. And in this scenario, this middle lug did not have, was not properly torqued. So that's one of the things we go through during the installation. We have our torque wrenches, torque screwdrivers, and good practice is something like this on the right-hand side, where we run around with a paint marker and we verify. That's basically kind of an industry, I guess, unofficial industry standard that we mark these terminals with the paint marker to indicate that they're properly torqued. So that's one of the other verifications we do during the installation. Make sure that people are using the torque wrenches, and make sure those wrenches are set to the proper setting as well. One of the things the designs may or may not show would be these trip hazards that we encounter after the fact. So it's inevitable that the conductors will need to cross these pathways at some point, but we really try to ensure that these hazards are mitigated in the initial system design. On the right, you can see the modules are completely obstructing access to the rooftop HVAC equipment. And again, just another design consideration that could have been avoided as well. In this case, we see a low-profile cable tray right over here, directly exposed to physical damage. It's also a trip hazard for workers accessing the roof. So again, these are just some considerations that during construction or ahead of construction, we should lay out how do we get conductors from this side to this side, and is this the best method? Again, beyond torquing the electrical connections, our mechanical terminations are equally as important. As we can see here, this system was already up and running, so it looks like they forgot to torque down a few of these module clamps. And again, here's an electrician using a torque wrench to ensure the hardware is tightened to the proper ratings. On the right, we see where bolts have been marked to indicate they're properly torqued. So again, this is what we're looking for as well. And lastly, outdoor rating for equipment. Another common issue is installing equipment that has not been rated for the environment. So this can be verified by specification sheets on the front end, but also a visual inspection after the equipment has been exposed to these conditions. So I'd say personally the most common misused components on a, I'll say outdoor rooftop solar installation is going to be this fitting here. This is called a bonding bushing, where basically it allows us to attach a ground wire to a metal conduit. 99% of the bonding bushings out there are not listed for outdoor use. And this, I guarantee this is probably after 1 or 2 months. That set screw rusts out and the whole component starts to corrode. And then after several years, we'll see something like this where it just completely, that copper and aluminum reaction will eat away at the aluminum. So these are the other considerations as well. So basically, in conclusion, commissioning PV systems consists of a variety of aspects. We have our equipment verification, where its components and quantities match the design documentation. So we're verifying that, yep, they installed what they said they would. Electrical testing, really that hands-on diving into it, verifying performance, verifying proper connections, helping identify installation issues. And then the last component, which could be independent in several cases that we do as well, are the compliance inspections. So the codes and standards, very similar to what the electrical or building inspector will look at. Also compliance with the design documentations, installation instruction, and industry best practices as well. So with that, I want to thank you very much for your time today. And I know we went through everything very quickly, but hopefully it provided a nice high-level overview. And at this point, I'll open it up to Liz if we had any questions.
Okay, Matt, we did have a couple of questions. Someone wanted to know if you had a brand of thermal imaging cameras that you preferred to work with.
Great question, and I'd say all of the most expensive brands I've used and have seen. And what I've really learned with the thermal imaging cameras is you're going to get what you pay for. We typically use cameras that go for around $8,000 or $9,000, and they're really really great quality. But the two things I'll note with thermal imaging are you can use them. The most common use is to find hot spots or temperature differential. You can also use them to read physical temperatures as well, and that's a lot harder to do. So I'd say almost anyone with a little bit of training could use them to identify a hot spot. But if you really want to use them beyond those limitations, there's what's called a certified infrared thermographer. I took some of those courses, and they get really, really involved. But I'd highly recommend something like that. If you're really serious about infrared thermography. But realistically, usually you're going to get what you pay for is the quick answer without endorsing any particular brands.
Okay, and then what is the average or a range average of ROI or simple payback periods for solar PV these days? And do you have any idea how dependent it is on economic feasibility or utility rebates or other incentives from state or federal governments?
Oh boy, that's a great question. So from my point of view, the ROI really is all over the place. There's a lot of people that will say that the state incentives or the government incentive really, obviously it really helps, and sometimes it can make or break a project. I don't think there's a real rule of thumb that I'm familiar with as far as the average ROI. Again, it's going to be different on commercial scale versus, residential, putting it on your house. There's just so many variables that I'd be misspeaking if I actually picked one, to be honest with you. But we know there's a lot of solar going in, so it must be, we're doing something right.
Good. Next question is, how did you handle the shade analysis when the deciduous trees are nearby and it's wintertime?
Gotcha. So basically the shade analysis when it's wintertime and the trees are nearby, basically this is where our job gets really interesting because we're all about being green, but now we're to a degree recommending or encouraging that we cut down trees, which doesn't sound right, but that's typically the only way we can address shading after the fact. Obviously, if it's shading from buildings, you can't really do much about that. But whether it's wintertime, let's say another part of that question, just so I fully answer it, in wintertime, you'll see the trees, but they won't have any leaves on them. So what we can do, and I kind of cruised past that slide, but we can manually cover those trees green. So basically to account for the full foliage. So that way, no matter what time of year we go and take this measurement, as long as we see the trees or at least tree branches, through that tool software after the fact, we can basically superimpose leaves on them to get a more accurate reading of the actual situation. So hopefully I answered the question thoroughly.
Yeah. Does the solar system bond to the building grounding electrical system?
The very quick answer is yes, and it depends on the addition of the electrical code and the different methods. That happens to be a controversial topic as you get into different editions of the code. But the very quick answer, all the metal parts on the solar will be bonded into the building's electrical system somehow. We'll leave it at that, basically.
Okay. And just before we lose any more people, and because I've gotten quite a few questions on this, yes, you will get a copy of the presentation slides. And yes, this is being recorded and will go up on the website under the recorded webinars in our resource section. Okay, a couple more questions here. When you are doing the roofing inspections, do you run into any problems with the mounting hardware?
Absolutely, yeah. So basically, and again, that's where the installation instructions really come into play because we need to ensure that the everything's compatible. We had a situation, actually, my coworker called me a few hours ago. They mixed brands on certain racking components, and turns out they violated a bunch of instructions, and now they're going to have to redo the installation. But yeah, that's absolutely super important.
Inverter placement was mentioned, but I don't think it was discussed. What should be considered with inverter placement?
Yes, thank you. I think you called me out because I probably deleted that slide to trim down the presentation. But realistically, so inverter placement, we want to make sure to meet the 2014 and 2017 electrical code, basically we're seeing installers bring inverters closer to the arrays, which means now these inverters have a high likelihood of being mounted on flat rooftops. So when we come to inverter placement, the two considerations are we want to make sure that they're not placed in direct sunlight if possible, which that's really hard to do if you're placing it on a rooftop. But there's components you can buy to add a little shade to the inverters so they're not facing the south side of a building or facing in direct sunlight. They lose efficiency a little bit. It's not a code issue, but it could be a performance issue. The other thing with inverter placement is we want to make sure the inverters are placed slightly far enough away from the solar panels so they don't cast a shadow on them. So I apologize from making that point, but then pulling that slide out. But that's basically the two main considerations with inverter placement. I guess the third one would be we want it close enough to the array that we don't have to deal with any voltage drop, which is basically long runs of wire with voltage losses in them as well. So apologize again.
No worries. Can you elaborate on the testing methods and the tests themselves? Or we might take too much time today on those.
Yeah, at a high level, basically it's an electrician with a bunch of fancy electrical meters and just testing the various system properties. And to stay organized, we use data sheets that we fill in, data collection forms, whether electronic or paper. That's my high-level answer. But yeah, maybe we could have a whole other tech talk on the physical electrical testing on solar PV systems. So it's a topic of its own.
Awesome. What kind of monitoring systems have you used in the past with emphasis, and how much have you relied on the data?
Great. We've seen a variety of monitoring systems. We're in a position where, since we don't physically install these systems, we don't particularly own the monitoring systems or work directly with them. What we would do is verify that the monitoring systems are producing or that they're connected properly. I don't have any particular brands as an example, but generally speaking, we would be looking at obvious power output, energy output, system power, temperature, sun exposure, and then your various electrical properties as well. So a good monitoring system will have typically all of that, all of the above.
Perfect. We're not going to be able to get to all the questions today. We're running out of our time. But I do want to thank you, Matt. This was an excellent presentation. We had probably our highest attendance, and no, in fact, it is our highest attendance to date for one of our Tech Talks. And we will get it up onto the website as quickly as possible. Thank you all for attending today. We're happy that these Tech Talks are proving to be a great member benefit, and we'll see you next month for next month's Tech Talk. Thanks, everyone. Have a great week.